Hello everyone, welcome back to Alkaline Hydroxide 784, and for the physics series today we will be covering the motion in a circle. I'm just happy that there's not that many points learning outcomes here because that hopefully would mean the video is not that long. I don't know. It could still be long because I remember my notes for this not being too that short either. Yeah. Anyway, so motion in a circle is a special kind of motion because it's not like you're not going in a straight line, but you're going around and around and around in a circle. I mean, not forever because the reality of this world is they can't really have a perpetual motion machine, but to some extent, for a pretty long time. So, what do we mean by motion in a circle? In physics here, yeah, like in A levels, we're mostly looking at uniform circular motion, and the other one is just the vertical one in the like the roller coaster style kind of vertical kind of circular motion, I guess. Um, so how does that work in a sense? I think before that we will first go through how a circle works in general, like the angles and stuff like that, and then we'll go to the actual physics part of it. Okay, so the first one is about the angular displacement. Well, so what is linear displacement? You just go straight on a line for like 10 meters, so your displacement is 10 meters. That's pretty straightforward. I mean, if you're going in the same direction for 10 meters, not go and then come back, then you end up with 0 meters of displacement. But here in a circle, we are moving in a circular path. So how do you calculate the distance? Well, of course, you use your circumference of a circle. And how do you do that? Well, if you use degrees, it's a bit confusing, right? Because like if you imagine the displacement as the arc, and you're moving, along that arc. If you use a degrees, then it's a bit annoying because the formula is 2 pi r, right? And you have to times it by the fraction of that degree over 360. But if you use radians, because 360 is equals to 2 pi in terms of radian, so 2 pi radian is one entire circle. And when you bring that into the equation of circumference, so you have 2 pi r times the angle over 2 pi. What do you think happens? The 2 pi here and the 2 pi there cancels out. So your angular displacement is actually just theta times r. So it's just the angle times your radius. Isn't that brilliant? It makes your equation so much less confusing, and it doesn't even include the pi. Wow. So let's say if you traveled 1 radian, then your displacement is 1 times the radius, which is wow, so brilliant. Okay, so so that's how you express your angular displacement in radians, kind of. So how do you change that into velocity? Divided by time, obviously. So yeah, if your angular displacement is r times theta, then your angular velocity is r times theta over the delta t. And in this scenario, we call that theta over the delta t as something that looks like a W. I do not remember how it's pronounced, unfortunately, but you know what I'm talking about, right? Yeah, this weird W looking thing. And that thing is called wait, what is it called? I know it has a name. I don't know what it's called, but it is defined as the radian per second. Like that's its unit. It's not just the angular, but the yeah, it's like the change with time, change of the angle with time in terms of radian per second, that is. So if you use this, then your velocity equals to r times that W thing, and you can use this to solve your questions if they ask you about angular velocity or anything about, that's just how it works. So I think that's pretty straightforward. Just use it in your question. So if you ask for angular velocity, that's what you try to do. You see, okay, so this thing is find the the W thing, and then you can get your velocity in no time. So yeah, so let's move on. Yeah, so let's move to the actual important stuff, because yeah, that is that is what the topic is about, the motion in a circle. So if you look at the motion in a circle, what does that actually mean? So if you're moving in a straight line, you're just moving in a straight line, right? There's a force in that same direction and you're just moving in that line. But if you're moving in a circle, how does it work? How do you make a straight line into a circle? Like, how do you bend it? Well, the idea is that you have a force that is perpendicular to you. So even though you're moving straight, the force is always perpendicular to you and you're being pulled into the circle. And the reason why it makes a circle is because the maths principles, that if you use the geometry one, if a tangent to a circle will always form a 90 degrees angle to the circle. So if you think about it, 90 degrees angle to the radius of the circle. Yeah, so in that sense, when you have a 90-degree force, a perpendicular force to your motion, then you are in essence creating a circular path, and that's why it works. It makes sense. So, and also you have to think about it in terms of the fact that the perpendicular force is always, it doesn't do any work in the direction that you're going in. So at the end of the day, there's no work done on your motion, and therefore you do not have a net force in the direction that you're actually moving per se, and that's why your magnitude of the speed doesn't change, but the velocity will always be changing because you still have a force acting on you perpendicular to you, which will change the direction of your velocity instead. And so we call this force the centripetal force, and along with it we have a centripetal acceleration based on the mass of the object. And this is what you call uniform motion in a circle. Yeah, so that's how it works. And yeah, that's pretty much it. You just need to explain why it's uniform motion. Like, you have to explain that the linear velocity will, like, the speed will always be the same, but the direction always changes. Hence the velocity magnitude will remain the same while its direction, but the velocity itself is changing. So in a way, you still have a force in the sense, but in that particular direction you have the same speed no matter what. I'm pretty sure your school notes will do a better job at giving you an explanation for this, so just use that and then write it down. But it's just for you to understand why it works. So now that you know that it works, what you do? Well, you can now derive the force and the acceleration for, because we have the displacement, we have the velocity, we need the acceleration, and in turn we can then find the force. So how do you get acceleration? We know that the acceleration is kind of like the displacement or time squared to some extent, but in this scenario it's not as straightforward as that. So we know in this scenario we have acceleration equals to v squared over radius. And the reason being is that if you think about it in terms of v square, v square will be having meter square second -2. So if you remove the radius from there, then you get kind of like acceleration units. So it should work in that sense. And the reason why it works in the other sense of the angle part is because because we are looking at the change of the angle as well. So you do need to times it along with the angle. while not really timesing the radius in the sense. So radius is always it's only involved once, no matter what, because it's pretty it's a constant, but the angular thing is the thing that gives that is the thing that is defined in the changing displacement or velocity of that object, whereas the radius is forever going to be the same. That's why you don't have the radius that squared or something like that in the sense. But yeah, that's not, you don't need to explain that. Just remember that the acceleration is equals to v squared over r, and likewise the force is equals to mv squared over r. So this is for specifically for centripetal acceleration and centripetal force. And yeah, that's pretty much it. Now let's move on to the stuff that's not written in the learning outcomes, but is still probably going to be tested anyway. So if you were to look at an object moving in like a horizontal plane in circular motion, these things should work pretty fine. And how you find the centripetal force is by drawing the free body diagram for the object. So like if the object has gravity in one way and then the tension in another way and so on and so forth, you must make sure that all the forces that are not perpendicular to the motion are all cancelled out. Basically the net force in those directions are all zero, but the force perpendicular to the object has a certain value, and that will then be the magnitude of your centripetal force. So like for example, if your tension is equal to the centripetal force, you can just write down the tension equals to the mv squared over r. Of course, write centripetal force first, and then in the next line you can put mv squared over r. Don't go straight into it. So yeah, that's how you solve your problems for a normal scenario. As for the vertical scenario, which is what I was mentioning earlier, they haven't really told it here because I don't know, it's not something, it's like a bit more of a application of what you know already. So in a vertical circular motion, you would have an object moving in the vertical plane, and that means that the force can change, or like the things that contribute to the centripetal force will change. So for example, if you have a if you have a box with some object inside it, and the box is attached with a string to the center, then of course you have your tension of the string, and you have the normal force of the box on the object, and then you have the gravity of the gravity acting on the object and the box as well. And from there you would know that at the very top the normal force will not be there, like it will be zero. I mean, if it's less than zero, then the object will fall down. So you must make sure that the normal force is at least zero in the scenario. And at the top, if the normal force is zero, let's say, and the weight and the tension are both added up to get the centripetal force, then at the bottom you would have the normal force plus the tension. The tension minus the weight plus the normal force will be equals to mv squared over r. So in this scenario, the tension of the string actually changes because the normal force is changing, and hence the tension changes. But the weight of the ball will not change, so yeah, that's the constant here. And the centripetal force magnitude will not change either, because that is also constant in terms of our calculation. So you can use this to find the tension at the two different heights in the sense. And you can also you can look at it in terms of energy as well, the energy change, by looking at the kinetic energy and the potential energy. So if you use the velocity, you can get kinetic energy, and if you use your height difference, you can use your potential energy. So from there you can calculate stuff based on the changes in the energies, as well as whatever I just mentioned just now, which is using your free body diagram and your common sense to figure out what exactly contributes to the centripetal force. And the final thing I want to talk about is about the scenario of the car. of a car going in curved motion. So if you are in a race car and you're driving down the F1 tracks, you would realize that there are some parts of the tracks, which the curved parts especially, which are raised up towards the audience, like the audience, it slopes downwards towards the center. And why is that the case? If you know, F1 cars are supposed to go really fast, and therefore the roads and the cars may not have that much friction per se, like so that they can move really fast. But if you move around the curve at such a high speed with not that much friction, in the scenario of a car going in a curve in a normal scenario, you would see that the friction actually helps with the centripetal, contributes to the centripetal force. So if you are going completely on a flat surface in a circular motion, the friction is what is keeping the car from moving inside in a way. It it prevents it from going toward the center. But if the wait, is it? Yeah, kind of. So the friction is what is preventing the car from moving away from its path. But in the scenario of it moving very fast, the speed can be so great that the friction cannot handle the car in a sense. In terms, it's like the normal force being zero. It has to balance out the centripetal force. Otherwise, the car will end up skidding, or it may go this way or that way or some other way. So in order to avoid this and to make it a little bit easier for the car to stay in the path, they raise up the surface so that you can use some of the like the weight or the normal force on the car to provide the to go against the centripetal force, or provide the centripetal force in a way, and to prevent the car from skidding out of way in a sense. So that's how it works. I hope the diagrams that I draw will make more sense than what I'm saying. But you get the point. You get the point. So I think that's the last thing I had to say. For the other smaller questions with more detailed things, if you have any questions like that, you can ask me in the comments below or in Reddit. If you found this video useful, you can press the like button and subscribe. And with that, I would like to say thank you and bye.